Last time, I showed you how to read data from a sensor using SPI with MicroPython and C. This time, I'm going to show you the exact same thing, but using I2C instead with the Raspberry Pi Pico. Let's jump in. I2C stands for Inter-Integrated Circuit. Analog Devices has a great article series on exactly how I2C works if you'd like to dig into the protocol. It's important to note that I2C is a bus protocol, which means we can have multiple devices attached to the same data and clock lines. While I2C can support multiple controllers or masters, you'll generally find just one on the bus. The other connected devices are peripheral or slave devices. These are things like your sensors. Both data and clock lines are open drain, which means that they must be pulled up to high by external pull-up resistors. The devices can only pull the lines low or let them float, which makes them return to logic high because of one of those pull-ups. Most breakout boards you come across, like the one we'll be using from Adafruit, will have the pull-up resistors already added, so we won't need to worry about them. To write to a device, the controller will send out the device's I2C address in the first 7 bits, followed by a 0 in the read or write bit slot. After each byte, the peripheral device will send an ACK bit back on the data line, letting the controller know that it's received the data. We can then send out data to the device. For many sensors, like our ADXL343 accelerometer, we'll need to send the address of the register we wish to write to, followed by another byte with the data. When it's done communicating, the controller issues a stop condition by releasing the clock line and then releasing the data line. Reading is similar, except that a 1 is written out for the read-write bit. After that, the peripheral device begins sending data out over the bus, and the controller responds with an ACK bit after each byte. When the controller is done reading, it sends a NACK bit and issues another stop condition on the lines. Most I2C devices are clocked at 100 or 400 kHz. However, you can sometimes find I2C devices that support 1 or 3.2 MHz. I2C is generally slower than SPI, but it uses less pins, which makes it good for things like low data rate sensors. Let's see how we can connect our sensor to the Raspberry Pi Pico using I2C. I'll be using the same sensor from the SPI episode. It's an ADXL343 accelerometer on a breakout board from Adafruit. However, instead of SPI, we'll be talking to it using I2C this time. The wiring is quite simple, as I2C uses just 2 wires for communication. We'll still need to connect 3.3 volts and ground in order to power the sensor and provide a reference potential. GPIO 16 is the data line, so we'll connect it to SDA. GPIO 17 is the clock line, so we'll connect that to SCL. Note that these pins are connected to the I2C 0 peripheral in the RP2040. Here is how I connected the Pico to the sensor. If you haven't already uploaded the MicroPython firmware to the Pico, you'll want to put the Pico into bootloader mode by holding the boot select button and plug in the USB cable. To upload the MicroPython firmware, the easiest method I found is to click on the button in the bottom right of Thonny. Make sure Raspberry Pi Pico is selected as your board. Click Configure Interpreter. Click Install or Update Firmware, and click Install in the pop-up window. This will download the latest firmware for MicroPython and upload it to the Pico. When it's done, you should see the REPL prompt in the shell. If you're working with raw I2C data from a sensor, I definitely recommend reading the datasheet. Let's first take a look at how I2C communication works for this sensor. Note that the chip select line on the sensor needs to be pulled high to communicate in I2C mode. The breakout board does this for us, so we don't need to worry about it. Additionally, the breakout board pulls the alt address line low, so the I2C address should be hex 53. To write to a register, we send out the sensor address first, followed by the register address. After that, we can send out the data to be written to the register. If we keep sending data, the sensor will write to consecutive registers after the one given by the address. If we want to read, we send out the sensor address followed by the register address. We then have the controller restart communication without issuing a stop condition, but set the read bit this time. Then the sensor will respond with data that's in the requested register. If we keep reading bytes, the sensor will send data from consecutive registers, which is a great way to read several registers with one I2C message. If a device ID is available on a peripheral, I like to read that first to make sure the communication works. It looks like the device ID for this sensor is hex E5. To tell the sensor to start taking measurements and get out of standby mode, we need to write a 1 to the measure bit in the power control register. Note that by default, the sensor's range is -2 to +2G. We can adjust that to plus or minus 16G by changing the range setting bits in the data format register. However, I'll leave it at the default range for this demo. The 3-axis acceleration data is held in the data X, Y, and Z registers. The paragraph for these registers is important as it tells us how to interpret the readings. Data for one axis is stored as a 16-bit signed value across two registers. The first register for each axis, such as data X0, contains the least significant byte. From this, we gather that we need to read the bytes in sequence, swap the order, and convert it to a signed integer using 2's complement. Let's see this in MicroPython first. This simple I2C scan program that we used in a previous video is super useful to see if we can communicate with the sensor and figure out what the I2C address is. When I run this, I should get some kind of address back in hex. It looks like the ADXL343 is configured to have an address of hex 53, so we'll use that. In a new program, we'll import machine, utime, ustruct, and sys. Then we need to define some constants to help us read and convert the accelerometer data into something useful. We'll use the I2C address that we discovered earlier. The device ID register should return hex E5, so we'll compare it to this known good value. Then we'll configure the I2C port. The RP2040 has two I2C peripherals, 0 and 1. The pins we're using are associated with I2C0, so we'll enter that here. We'll define the pins and set the frequency to 400 kHz. Next, we'll define our register write and register read functions. What's funny is that these end up just being wrappers for the read to mem and read from mem functions already built into MicroPython. The only difference is that I make sure data is converted to a byte array in regwrite. And in regread, I do a simple check on the n bytes parameter to make sure it's at least 1. In our main program, we'll read from the device ID register first and compare the return value to the known good ID. If they don't match, we'll print an error message and exit the program. Next, we read from the power control register and set the measure bit to 1, which is bit 3. Note that I need to convert the read data to an integer first and then bitwise OR it with our bit field. By doing this, we don't change any of the other bit values in that register. Then we write it back to the power control register. I like to do a simple test where I read and print the value of the register before and after the write operation to make sure that we successfully made the change. I'll then sleep for 2 seconds so that we can see that register value being updated. Finally, we loop forever printing out the values of the X, Y, and Z registers. To do that, we first perform a 6-byte consecutive read starting with the data X0 register. We then use ustruct to unpack the data and convert each pair of bytes into a signed 16-bit integer. After that, we do a little math to convert the raw reading to something that's useful, like meters per second squared, and print the results. I like to add a little bit of delay between readings so that we get a chance to see what's happening. I'll save this program somewhere on my computer and start running it. If everything works, it should print out the contents of the power control register twice to show that we can successfully write to it. Then it should start spitting out accelerometer data. If I move the board around, the measurements should change to reflect that. If I hold one of the axes perpendicular to the ground, that axis should give me plus or minus 9.8 meters per second squared. Let's do the same thing but using the Pico C SDK. I recommend following my guide on maker.io to set up VS Code and the required toolchain to develop code for the Pico. Navigate to your Pico projects folder. In a previous video, I showed you how to create a simple Blink program, which makes for a great template. Copy that folder and rename it to something like ADXL343_I2C. You'll also want to delete the build folder in there so we can run CMake from scratch. Open VS Code and tell it to open the folder we just made. In CMake lists, change the project name from Blink to something like ADXL343_I2C. We'll also want to include the C SDK I2C library, so add hardware_I2C in the target link libraries. If you're using Pico Probe for debugging, you'll probably want to leave UART enabled as the debugging port. Otherwise, I recommend enabling the USB port. Save this file. If you do not have the CMake extension installed, you'll want to run CMake from the command line as I showed you in a previous video. If you do, select ARM GCC as your kit and click the CMake button at the bottom. Click on the debug release and CMake should run, creating a build folder in your project directory. In main.c, delete everything. Let's include stdio, Pico stdlib, and hardware I2C as our libraries. We'll also want to define some constants, including the I2C address and register addresses. Just like in the MicroPython example, we'll want to compare the device ID to the known good value and have some constants we can use to convert raw accelerometer values to usable numbers. While not strictly necessary, I'll declare my functions first. This is to show you how you might make this into something like a library. These function prototypes would be in a .h file that you would want to include in your build process. To write to one or more registers, we'll first make sure the caller is sending at least 1 byte. We'll construct a message consisting of the register address and whatever data is sent to this function in the buffer. Then we'll use the I2C write blocking function to send this message out over the I2C lines. Reading from a register or consecutive set of registers is easier. We'll check the desired number of bytes first and then simply call the I2C write function with the register address as our data. The last true argument of this function tells the I2C not to send out a stop condition and it should keep the bus open. So we immediately send out a read command just after and store the received data in the provided buffer. In main, we define our pins and tell the RP2040 that we want to use the I2C0 peripheral as that's the one associated with pins 16 and 17. We create a buffer and initialize the serial port. We then configure the I2C port to operate at 400 kHz. We tell the RP2040 to connect our 2 pins to their associated I2C functions. Then we read the device ID and compare it to our constant value. If they aren't equal, we print an error and stall the processor. Next, we read from the power control register. We set the measure bit, which is bit 3, and write the value back to that register. I'll print out the value of the power control register before and after the write, but we may miss it if we start the serial terminal too late. I'll wait for a few seconds before going into the forever loop. Here, I'll read the consecutive X, Y, and Z data registers and then convert the returned pairs of bytes into 16-bit signed integers. Next, I'll convert those raw readings into useful measurements with meters per second squared units. Finally, I'll print the results and sleep the processor for 1/10 of a second. Save this file. I'll build the project with Make. Note that if you don't have these extensions installed, you will probably have to do it manually from the command line. If you have the Pico probe connected for debugging, you can simply press the debug button to start running the program. If not, you'll need to put your Pico into bootloader mode so that it will enumerate as a mass storage device on your computer. When Make is done, copy the .uf2 file in the build folder to the rpi-rp2 drive. This should cause the Pico to reset and start running your program. Open your favorite serial program and connect it to the Pico with a baud rate of 115,200. We'll probably miss the power control register values, but that's okay. You should hopefully see the X, Y, and Z accelerometer values being printed to the screen. Move the board around and watch them change. As you can see, I2C and SPI can be kind of similar when it comes to reading data from a sensor. I hope these videos have helped you get started using these communication protocols and getting your Raspberry Pi Pico to talk to other hardware. On the next episode, I'm going to take SPI a step further and show you how to read and write files from an SD card so you can, say, make something like a data logger. See you then, and happy hacking!